All right, so thank you guys for coming to this lesson. So as you can see here, the goal for today's lesson is that we can calculate equivalent. Oh, sorry, is that we can calculate equivalent dose. Now, I did have a look at the learning task from last week, and I see that I've got one submission for the radiation calculation worksheets. Um, okay, so the rest I need you guys to do it. I know that we have gone through um, like half of the worksheets, at least we went through the examples. Okay. If you have not done it, then well, we have double today, so you guys can use the time to do it. Okay, and then you can submit it to the learning task week 5 and 6. Okay. Now, I'm going to go through the next lesson, so lesson 7 on equivalent dose. Okay, and then I would let you guys go and do your work for the worksheets. Okay, so and there will be one more worksheet that you need to do for today's lesson. All right, so let's go through this. All right, so goal is that we can calculate equivalent dose. Um, all right, so our APK for today is how much radiation are we exposed to every day? So have a think about it, guys, and then if you think you know the answer, then you can put it in chat. You can also use the image there as sort of like a guide for you. Okay. So I'm going to give people another probably 30 seconds to think about it, and then we're going to move on. You may see it from the picture that we got, radiation everywhere in our in our daily lives, right? So, just being outside, you're going to get cosmic rays. Um, we also get radiation from the food that we eat, the water that we drink, um, and yeah, like the rocks and the soil around us as well. Okay, so in a way, our body has evolved to to what's the word? What's the correct word to use here? Tolerate a certain amount of radiation. Okay, and if it goes any more than that tolerance, then obviously it's going to have an adverse effect on our body. All right, so um, there's a video here. You may have watched it in Year 9 Science. It's a really good video. I do recommend that you watch it if you haven't. Okay, I'll let you watch it. If you want there. Again, I think it's a really good one. It's very interesting. But this is the main thing that uh, we're going to go through today. Okay. Now, I know that we have written the equation. Okay. We have written the equation at least, but I would also like you guys to write down sort of like the definition later on. Okay. I'm just going to go through the notes very quickly so that you guys can go and do your work. Okay. So when you do that, copy down the notes for me. So first one, we've got the absorbed dose. Okay, so the absorbed dose is the amount of energy absorbed by each kilogram of tissue being irradiated. Okay, so what that means is that, say for example, you get an X-ray. The X-ray is going to have a certain amount of energy. Okay, and if you remember when we talk about the electromagnetic radiation, like X-ray, gamma rays, they have high amounts of energy, okay, then say for example, if I've got a broken arm, okay, and I go and get an X-ray, well, they're just going to X-ray the arm part. They're not going to X-ray the whole body, right? So this is the only part that would be exposed to radiation. So they need to sort of like have an estimation of, well, how much would this part weigh, okay? So they've got calculations. So say if they know your body mass, okay, how much your body weighs, then they would then work out, okay, so the arm bit would probably be, say, 10% of your body mass, okay? And then they can work out, okay, what would the arm be? It's probably going to be less than 10%. That was just a figure I came up, you know, at the top of my head, okay? And then they would calculate the amount of absorbed dose, and they see, is it too much, is it too little, okay? So as you can see from the equation, okay, it's the energy absorbed divided by the body mass. So let's break down this formula a little bit, okay? So if you got a certain amount of energy, okay, so let's say um, all of us go to get an X-ray, okay? We would X-ray the same body parts, um, so they would use the same amount of energy, okay? Now, I'm 70 kilograms, okay? Last time I checked, I'm 70 kilograms. My absorbed dose is going to be different to a person who weighs 60 kilograms. It's going to be different to a person who weighs 50 kilograms, okay? So because my body mass is 70, is higher than 60, higher than 50, I can take a bit more dose, okay? So my absorbed dose is not going to be high in comparison to a person who may weigh 50 kilograms. They would have a higher absorbed dose, okay? And this is particularly important when you think about how a person is treated for, say, for example, cancer, and um, they have to calculate all the risk. Okay, how much radiation can this person take? Okay, um, now we also learned that different type of radiations causes different amount of damage to the body. Okay, so we then need to do another calculation, which is called the equivalent dose. So the equivalent dose would take into account the different styles of damage caused by the different radiations. Okay, so you can see at the table there. So gamma, the Q there, that's the quality factor. So sort of like the damage, how damaging it is. So gamma, as you can see, there is a 1. Beta is also a 1, so they are the least damaging radiation. Um, gamma is a bit less damaging than beta, but we're just going to use 1. Neutron, if it's a, we haven't learned anything about neutrons radiations, so I'm going to skip these, but as you can see, they're 5 and 20, depending on the speed, and then alpha is a 20. So alpha is the most damaging type of radiation. So the equation we use is we take the absorbed dose, so whatever we calculated before, and then we multiply by the quality factor, okay? And the unit for equivalence dose are sieverts. Now, here's a note, and you don't have to write down this bit here with the notes. So in practice, in reality, the gray unit for absorbed dose and the sieverts for equivalent dose, they are quite large. Okay, so 1 gray and 1 sievert are quite a large amount. If you get 1 sievert amount of radiation, you would actually develop radiation sickness, and which can lead to death. Okay, so normally we don't use that large amount of dose, and normally we would deal with things like milligray and microgray, millisieverts and microsieverts. Okay, so um, for anyone who's interested, a milli, okay, so if you think about a millimeter, okay, so a milli, there's so 1 gray would contain 1,000 milligray, and also that's going to be 1 million microgray. So you can see here that we are dealing with very, very small scale. And that's what we want. We don't want that much radiation to our body. Okay, so same thing with sievert. So 1 sievert would be 1,000 millisievert, and that is 1 million microsievert. Okay, all right. So with that, let's do the worksheet. I'm going to go through the examples with you guys, and then I'll let you guys do the worksheets by yourself. So go back here, download the worksheets. Okay. Now, if you feel like you can do the worksheet by yourself, then just go ahead, stay on the WebEx, but go ahead and try to do it yourself, and maybe you can offer the answer for some of these questions. Okay, so so here what we have, example 1, we have got a 60 kilogram person absorb 0.054 joules of energy due to ionizing radiation, and we need to calculate the absorbed dose. So remember, absorbed dose is equal to the amount of energy, okay, divided by the mass of the person. Okay, so I guess in this case they've got like a full, maybe X-ray, a full body X-ray, or maybe they're going through treatments and it treats the whole body. Okay, so we have 0.054 joules divided by 60 kilograms, and you just have to put it into your calculator and you can work it out. So using my calculator, 0.054 divided by 60. Okay, I get an answer of 0.0009 gray. Okay, so very, very small scale. Now, if you want to, you can also convert this into milligray. So remember that there is 1,000 milligray in 1 gray. So if we times it by 1,000, we would get 0.9 milligray. Okay, and that is a very small dose. Then question B asks, what would be the dose equivalent? So equivalent dose would be the absorbed dose multiplied by the quality factor. Okay, and absorbed dose is from the question before, so 0.9 milligray and multiply by the quality factor. So we're going to have a look at what the quality factor is for gamma rays. So if we go back to our PowerPoint here, you guys may remember, but gamma ray has a quality factor of 1. So we times that by 1. And that would give us an answer of 0.9. Now because we're using milligray, it's going to be millisievert for our answer. Okay. Then question C says, what would be the dose equivalence if the energy was delivered by an alpha particles? So we're going to use the same equation as before here. So absorbed dose times by the quality factor. The absorbed dose is 0.9 milligrams again. And the quality factor for alpha, if we go back to our PowerPoint here, is 20. So we're going to multiply this by 20. And that would give us 18 milligray. So as you can see, that is much more, sorry, not gray, sieverts. But it's going to be much more, it's a larger amount of dose. Okay. And then which would cause more biological damage to the person? So it's going to be the alpha particles. Okay. And you can say that because the person would receive if I can spell correctly, receive a dose of 18 millisievert in comparison to just 0.9 millisievert with gamma. Okay. So what I've done there is I used the answer from the previous 2 questions to justify my answer. Okay. Then example 2 here. So on average, each crew member on the Apollo space mission received a dose of 12 millisieverts, while in space, the exposure was mainly electron. Now, if you remember electron, that would be beta. Okay, fast-moving electrons would be beta radiation, and we also have gamma radiation as well. So estimate the astronaut mass and determine how much energy each astronaut absorbed. Okay, so so we are given the equivalent dose. I'm struggling to spell today, guys. Okay, so we are given the equivalent dose, which is 12 millisievert, and we are asked for the amount of energy. Okay, so how can we do that? If we go back to our equations here, we've got 2 equations, okay? One for absorbed dose and one for equivalent dose. So in order to find out energy, you need to know the mass and you need to know the absorbed dose. Okay, so the question tells us to sort of like estimate the mass for an astronaut. Okay, for an estimation, you guys can have sort of like a guess of like any reasonable amount of mass would be fine. Okay, obviously they can't be too tiny and they can't be too heavy either, right? So around around 650, maybe 50 to around 80 kilograms would be all right. Uh, or you can also have a look on Google, like say the average mass of an astronaut. Okay, so we can do that. For the absorbed dose, what we can do is we're going to work it out from the equivalent dose. Okay, so if we use the equation for equivalent dose, oh my goodness, I am really struggling to spell today. Okay, so equivalent dose is equal to the absorbed. Oh, wow. Wow, Mr. Wow, Mr. N. Absorbed dose multiplied by the quantity, or Q. Okay, I'm just going to say Q there because I'm running out of space. So we got 12 millisieverts here. We are looking for this amount. Now we know the radiation is beta and gamma. So that's going to be a quantity of 1. So what number multiplied by 1 gives you 12? That's going to be 12, yeah? So the absorbed dose would be 12. Now remember, for dose, it's going to be a unit of gray. And since we're dealing with millisievert, it's going to be milligray. And then from here, we can work out the energy. So the absorbed dose is equal to energy divided by the mass. Okay, and we have 12 equal to something that we're going to try and find out, divided by the mass here. And let's have a look at what's an average mass of an astronaut is. Average mass of an astronaut. So they're between 50 and 95. Okay, so I was somewhere in there. And 26 mass of basic forensic. Uh, this is medicine, and you need to do calculation when you deal with medicine. You don't want to give people too much of a dose. Okay, so mass between 50 and 95. So how much should we use, guys? Any suggestion? Pick a number between 50 and 95. 70. 70 sounds good. Okay, so we've got 70 there. So what number divided by 70 gives you 12? Okay, and we can do a bit of algebra to work it out. So that's going to be 70 times 12. Okay, so that's going to be I think I've done that correctly. Okay, and the unit we're going to use for this is going to be millijoules. So you can see here I'm using milli throughout. Okay, so millijoules, and that is basically 0.84 joules if you want to convert it. Okay, so I know there's a bit of math there, guys, and a bit of algebra. Okay, like I said, this is because when you study medicine, you don't want to give people the wrong dose. Okay, there have been cases where the nurse or the doctor they they did the wrong calculation and they give the patient the wrong dose. They give them too much or too little, and that affects the patients, and you don't want to do that, right? So math is very important when you deal with medicine, guys. Okay, so so we've done the two examples here. So we've gone through how to calculate the absorbed dose and the equivalence dose. Then also we have gone through how to calculate how to calculate the energy. So we go backwards from the equivalence dose. We calculate the absorbed dose and then back to the energy. Okay, so a little bit of algebra. Okay, but I'm sure that you guys can do it. If you need help, feel free to ask me. So I'm going to let you guys do the questions here. There are 8 questions, and question 8 is a bit of an extension. Okay, and if you have done everything and you want um, a bit of an extension, then you can also do this work here on Education Perfect. Now it is optional. This is for, like I said, this is for the people who want to consolidate and extend their knowledge. Okay, so I know that I kept you guys for quite long. Thank you for your patience. Thank you for staying and listen to me. Um, if you guys need any help, please feel free to ask me. All right.